All right, so today we're going to start section 5.3, which is the Schmidt process. And so in all of chapter 5, we've been talking about and showing how when we have a basis that is orthogonal, that means all of the basis vectors meet at right angles, it makes a lot of our computations easier. And so it's desirable to have an orthogonal basis. The other thing that we saw in section 5.1 is that sometimes it's even better to not only be orthogonal, meeting at right angles, but also to be, for all of those vectors to be unit vectors. And so that is called an orthonormal basis. And so we'll be talking about both of those things with this Schmidt process. So an orthogonal basis is where all the basis vectors meet at right angles. And an orthonormal basis, that is a basis, it's an orthogonal basis of unit vectors. And we talked a little bit before about what basis meant. Remember, if we want to recall, what does a basis mean? A basis means that, that the vectors are linearly independent and spanning. So they span whatever subspace it is that they're spanning. So they span the whole subspace, and they are linearly independent of one another. And we had a theorem that said if a set is orthogonal, we automatically get linearly independent. So we don't have to check linear independence if we have an orthogonal basis. So let me just write that down. Orthogonal sets are linearly independent. So that's another of the upsides of having an orthogonal set, an orthogonal basis, is that you know that they are going to be linearly independent. So what the Schmidt process is going to do is it's going to allow us to take a basis that is not orthogonal and turn it into a basis that is orthogonal. So we're going to be, kind of straightening out that basis. And so we're going to have to use some of the ideas that we had already just previously discussed. And so one idea that we had discussed is the idea of a projection. So projection of some vector v onto a vector u. So what that would be is if I have some vector v here and some vector u here, then the projection of v onto u is going to be this vector that is parallel to u, so it's a scalar multiple of u, and it's kind of the component of v that is running along u. And so what we see here is that we can compose v into two parts. We have this part, which is the projection onto u of the vector v, and then we have this part here, which we were calling the perpendicular part. So this we would call the perp onto u of the vector v. It's perpendicular with u. And so we can see that v can be decomposed into these two parts. So v is equal to the sum of that projection vector plus the perpendicular part. And so that is going to be the idea of how we're going to be able to straighten out the basis. So the idea is going to be we're going to start with the first vector, and then we'll take a second vector, and we're going to take the part of that second vector that is perpendicular to our original vector, and that we're going to use that as our new second vector and go on from there. And so that is going to be the idea of the Gram-Schmidt process. So let's start with an example, and then we'll write out the Gram-Schmidt process in its entirety. So let's do example, oops, let me be using black. So example 512, okay, so it says let the subspace W be the span of the vectors x1 and x2, where x1 is equal to 1, 1, 0, and x2 is equal to negative 2, 0, 1. And so I can check to see if they are orthogonal to one another, and I know that whether or not they're orthogonal by whether their dot product is 0. So if I do x1 dot x2, that gives me 1 times negative 2, so negative 2, 1 times 0, which is 0, 0 times 1, which is 0. So that's just negative 2 is the dot product. So that means that they are not orthogonal. Okay, and this is seeming really familiar. I think this is maybe the same example we did in class last time, but anyway. So our instructions here are to form an orthogonal basis. Basis for W. So what I want is I want vectors that span all of W, but are orthogonal to one another. And so I can let, so we're going to start with x1. I want to get a second vector that is perpendicular to x1 by taking the component of x2 that is perpendicular to x1. Okay, and so how do we find that perpendicular bit? Well, I can do the projection of x2 onto x1, and then I can subtract that off, and that will leave me with the perpendicular bit. So in other words, if I look up here at this relationship, I can say that the perpendicular part is going to be equal to the original V minus the projection part. And so that's the way I'll be able to find the part that is perpendicular to x1. And so let's go. So we're going to let v1 be x1, which is just 1, 1, 1, 0. And then we want to do, we're going to find the projection of onto v1 of the vector v2. I did that notation funny. I just want to put a v1 under here. Sorry. Well, let me not introduce this new notation just yet. Let's go ahead and find the, let's go ahead and project x2 onto x1. So the projection onto x1 of the vector x2 is going to be equal to, I'm going to do, oh, I didn't write it down up here. Let me write it down here. So it's projection, I just drew the picture. It's going to be u dot v over u dot u, and that's all going to make a constant. And then that's the constant that I multiply u by to get that scaled down bit. Or maybe it's scaled up, depending on the size of the vectors. Okay, so the projection onto x1 of the vector x2 is going to be x1 dot x2 over x1 dot x1 times x1. Okay, so let's compute this constant here. So if I do x1 dot x2, I already did that. It was negative 2. And then x1 dot x1 is going to be 1 times 1 plus 1 times 1 plus 0 times 0. So that's going to be 2. And then I'm going to multiply that by x1, which is 1, 1, 0. So that gives me, that's just a negative 1, so it's going to give me negative 1, negative 1, 0. And so that is the projection onto x1 of x2. So that's this, so let me highlight that with, let's see, I was doing the projection part in blue. So this part here is going to be the blue part. If I think about, this is my x1, and this is my x2, and this picture is not in the right dimension, so, but I'm drawing it like this so you can kind of see the parts. So what I found there is the the parallel part. So this is the projection onto x1 of x2. And then this is the perpendicular part. So for that perpendicular, how do I find that perpendicular part? Well, I'm going to take the vector x2, so I can get that perpendicular part by taking my x2 minus the projection part. And so what is that? Well, my x2 was negative 2, 0, 1, and I want to subtract off negative 1, negative 1, 0. So it's a lot of negatives here. So yeah, I definitely did this in class on Tuesday. So negative 2 minus negative 1, so it's negative 2 plus 1, so that's negative 1. 0 minus negative 1, so that's going to be 1, and then 1 minus 0 is 1. Okay, and so that is my perpendicular part. So I can let V1 be x1, which is this guy, 1, 1, 0, and then V2 can be that perpendicular, which is negative 1, 1, 1. So you might wonder, is this an orthonormal basis? So are these normal vectors? Well, I want to look at the length of that vector. So the magnitude of V1 is equal to the square root of 1 squared plus 1 squared plus 0 squared. And that is actually the square root of 2. So it is not, a unit vector. But I can make it into a unit vector by scaling it by this, by 1 over its magnitude. So if I want to make an orthonormal basis, I can take V1, let's see, I wonder if the book uses different notation. Oh, here we go. Yeah. So I think the book actually changes the notation here. So I can say Q1 is going to be V1 over the magnitude of V1. So I'm going to have 1 over square root of 2 multiplied by my V1, which is minus 1, 1. Oh, shoot. No, it's 1, 1, 0. Sorry. So my Q1 is actually 1 over root 2, 1 over root 2, 0. And my Q2 is going to be 1 over the magnitude of V2 times V2, which is 1, 1, 1. And so when I find the magnitude of that, it's going to be square root of negative 1 squared plus 1 squared plus 1 squared. So it's going to be square root of 3. So that's equal to 1 over root 3 times minus 1, 1, 1. So it's going to be minus 1 over root 3, 1 over root 3, 1 over root 3. So now these two, Q1 and Q2, are not only are they orthogonal, but they are also unit vectors. So they form an orthonormal basis. So now Q1 and Q2 form an orthonormal basis.